Gang Fu. Dr. Gang Fu did his undergrad, master's, and PhD from Xiamen University in 2004, being advised by Hugh Liu and Jin Yu, and studied the selective CH activation over transition metal oxides. And he stayed on at Xiamen University, had some research stay in France at the École Normale Supérieure de Lyon. And since 2016, he's now full professor at Xiamen University. And he's going to talk today about catalysis at the interface coordination chemistry view. Thank you.
Thank you, Chairman. Thank you, the organizer, to give me the opportunity to stand here to introduce our recent work. And I feel that it's a great honor, and I feel it's a high pressure to here. The topic of my presentation is the catalysis at the interface from the coordination of chemistry view. My name is Gang Fu from Xiamen University. This is the joint work between the experiment and the theory. I'm from the theoretical side. So, as you can see, this is the heterogeneous supported catalysis. You can see the heterogeneous catalysis is very complex. Why? You can see that there are different exposing phases. There are terrestrial side, static side, and quantum side. And as the metal particle is supported on the usually on the metal oxide, so that involve the metal oxide interface here. And we usually introduced organic ligand during the synthesis. So we also have the organic metal organic interface here. As Bruce Gates have addressed it today, the support can be looked at ligand. So the catalytic behavior of the metal particle it can be controlled by the coordination environment. So, my talk consists of 3 parts. The first part is the metal organic ligand interface. As I have stated, during synthesis, you usually add some organic surfactant to synthesize the unique nanoparticle. And for the catalyst, when you test the catalytic performance, usually you remove the ligand to expose more active site. But when you keep the organic ligand on the surface, maybe you have some unique selectivity. In this case, it's a platinum copper nanoparticle with the ligand is the organic amide. Okay. Here we use the selective hydrogenation of the aldehyde as the model of reaction. This one is the alpha beta unsaturated compound. The result product is the unsaturated alcohol, and the saturated aldehyde and saturated alcohol is the byproduct. How to control the hydrogenation? Only in this direction, on the CO bond hydrogenation, but not this direction. It's very different. Yeah. When you use the catalyst with organic modification, we have, because the organic ligand we block some active sites, so the reactivity is very low, but selectivity is very high. We can replace the organic amide by using the salt amide, such as the C12 amide, C8 amide, and C4 amide. The reactivity increased, but the selectivity decreased. To get more insight about this system, we perform the DFT calculations. Here, for the clean surface, you can see that CC bond association on the 100 surface and 11 surface is more favorable than the CO bond association. So for the clean surface, the main product is CC bond hydrogenation product. So the reaction goes through this way, but not on this. So the clean surface is not a good catalyst for the CO bond hydrogenation. Here we have considered two configurations for the organic amide absorption. The difference between them is the time angle. This is about 13, this is about 60. Yeah, for the amide with the short carbon chain, the absorption energy between these two configurations is very similar. The absorption energy is very similar. But for the organic amide, because it's very long chain, this one is close compact. So the absorption energy in this configuration is more stable than this one. Yeah. We also calculate the rotation barrier. For the short carbon chain, the rotation is feasible. The barrier is about only 0.1. And for the organic amide, the rotation requires about 2.8 eV. So it cannot rotate on the surface. So the organic amide can form the radial ring on the surface. It can create some unique site with stereo effect. And here we can compare the similar aldehyde absorption on the C4 amide modified surface and organic amide modified surface. You can see that in this case, because the C4 amide can be rotated, the surface is still open for the C4 aldehyde. So CC4 still absorbs very strongly. And in this case, the organic amide only enter into the array with his CO bond. And CC bond is directed away from surface. So the reaction goes through this way, because only CO bond can be hydrogenated. And CC bond avoid the CC bond hydrogenation. So it's go this way, and also avoid the hydrogenation of CC. Yes, we have published it at 2012. At that time, there are other groups use sulfide by Berlin and by Sommergel, and here use the peptide and use the alkene to modify the surface to improve the selectivity. But in all these cases, we improve the selectivity by using the stereotic effect. How can I use the electronic effect to control the selectivity? It's a very important question. So the second example is the selective hydrogenation of nitrobenzene. As you know, the hydrogenation of nitrobenzene is the final product is the aniline. Because from the viewpoint of thermodynamics, the most stable hydrogen product is the aniline. However, when we use the arch-thin PT nanowire here, established here, the main product hydrogenation is not aniline, it's a hydroxy aniline. So the selectivity to the unstable partial hydrogenated product is too strong. Why? Here is the model of the arch-thin PT nanowire. Because experiment, the diameter of the PT nanowire is about 1 eV, so we construct the reliable model. If you synthesize maybe the nanowire with 5 to 10 nanometer, no, we cannot construct such a reliable model because it's too big. But in our case, we can construct a reliable model for this one. However, when we compare the absorption energy of different and content benzene on the PT nanowire and the PT111, PT100, and PT110, you can see that the absorption energy on this surface is did not. There is no significant difference between them. So all of them can strongly absorb on the surface. What's the origin of the selectivity? Yeah? We should miss something. Yes. Here. Because during synthesis, we use acid diamide. And the acid diamide is strongly absorbed on the artificial Peter nanowire. It still has acid diamide. And with acid diamide, the surface becomes negative charge. So here the blue indicates the surface negative charge rather than the zero. It's no mechanical. So here we have example. In substance here we have PT. This is the PTM bond here. And we also use the CO shaping. Yes, you can see that this is the CO, the CO distortion. Peak is here, is shift here to here. Yeah. So this is demonstrated is electronic effect. We can modify the PD nanowire, the electron state of the PD nanowire. Here's the mechanism. Because the surface has been heavily coated by the acid diamide, the surface becomes negative charge. So it can change the absorption behavior of different substrates. For the nitrogen, it can absorb on the surface with highly coated acid diamide. When it comes to here, it opens one hand because it's collecting absorption on the surface. It can open one hand, it can enter to get absorption. And for the nitrogen benzene, it can also get absorption here. But when the hydrogen goes to the hydrogen energy, yeah, you can see that the absorption energy is positive. It cannot absorption on the surface again. So it can be kicked out from the surface. Switch off the hydrogenation reaction. So the reaction stops at the hydrogen energy. So the conclusion is the strong absorption of the acid diamide, it creates an enriched surface, which disfavors the absorption of the hydrogen energy. Yes? So we can come back. The key is the surface has been heavily coated by the acid diamide. It's not a nanowave. It's not a nano effect. It's electronic effect. Or it's interface effect. So we can use this understanding. We can optimize the conversion. Look, here is PD black. You know the PD black has the selectivity towards the enemy. Yeah. One way use PD black, we use a modified PD black. How to do this? Use PD black is on the PT acid diamide with the PT acid diamide precursor. We use the in situ reduction to generate many atom, PT atom on the surface, and with the acid diamide absorption on the surface. In this case, yeah, you can see that we can also get very high selectivity toward hydrogen energy. So it's electronic effect. The second part is metal oxide interface. As you know, the support effect is one of the most important questions in heterogeneous catalysis, because many important reactions take place on the metal oxide interface. However, you can see that limited information will come from the interface, because more information will come from metal and the metal oxide, but limited information comes from it. So it's still a great challenge to characteristic the information from the intermediate. We had proposed two strategies. The first one, we can reduce the support. Yes, we can use the support on the metal. We can grow some metal oxide on the noble metal. In this case, all the metal oxide is at the interface. And we can, in the second step, we can reduce the particle size of the metal from the nanoparticle to the thin atom. So all the thin atom is surrounded by the metal oxide. Here is the example. We can use the iron hydroxide on the planet. Here we use the CO oxidation for the model reaction. You can see that when we use the PT, another particle, the reaction temperature is for the 100% conversion is very high. It's about 100 degrees C. When we use some submolar iron hydroxide, all the planet inside, you can see that the temperature will be decreased. We have room temperature, or we can get the room temperature of 100% conversion. So it's low temperature CO oxidation. Yeah. So from the XPS, we can see that iron is in the 3+. And OH group, the ratio of OH group to O is about 9:1. From the ISS, is ion scattering spectroscopy. We can see that PT is still exposed on the surface. So we build such models. In this model, here is the ion hydroxide, and here is the PT. For the CO oxidation, one of the key parameters is the absorption engine of CO and O2. For the clean surface, it's why the H side. PT is of the step side for the PT nanoparticle. We can see that the absorption engine of CO is much stronger than O2. So in this case, we cannot achieve low temperature CO oxidation. Even we count the planet with the iron oxide, the CO absorption is still much stronger than O2. When we remove one hydrogen here, the O2 absorption becomes much stronger. So O2 can be stabilized at interface. So why the interface is very important? It can stabilize the O2 absorption. Yeah. How to create the vacancy? Yeah. In our mechanism, the vacancy can be created in situ. And the first step, we have the iron hydroxide platinum, such as the interface structure. And here, CO absorption on the platinum. It can react with the OH to give COH, and then COH lost the hydrogen to give CO2 to generate a vacancy here. And such vacancy is able to activate the oxygen. So we have got the OH species, and the second CO will react with the OH species to make another CO2 and recover the interface structure. So we complete the catalytic cycle. How to conform this mechanism? Because in this case, we propose the interfacial hydrogen is very important. Yes. Here we have some experimental evidence. The first one, when we use the acid treat, because acid treat can remove the hydroxy group. Yeah, this is the catalysis. Without acid treat, it's all very good, very good performance. When with the acid treatment, you can see that no reaction. So the oxygen can be removed. The second one, we should use the humid CO and O2, the gas, because when we remove the water, the reactivity drops very fast. Yes, and we also use the isotopic level experiments. We use the O18 enriched water and O18 enriched water in the reactant, in the mixed gas, and we can get the O18 enriched carbon dioxide. So here is our proposal is here. In the commercial catalysis, the interface is limited. When we grow the iron oxide on the metal, on a noble metal, we can enrich the interface. And finally, we develop a new strategy. We can synthesize the sub-nano alloys with platinum, alloy, and nickel, and put this in a reaction condition. That we can get a hybrid structure with 3D interface. Yeah. Then this one can be worked for more than 1 month for CO oxidation without any decay. Yes, this paper published in the Science in 2014, and the complete computation work has been published in the Private Discuss. Because the support, when we use support effect, we also the support effect on the reducible oxide from the iron oxide, titanium oxide. How about the irreducible oxide? For example, the silicon. The silicon oxide, your copper silicon, is very good catalyst for the hydrogenation of the dimethyl oscillate. This is the final step from the core to the ethylene glycol. It's very important industry process now in China. This is the final step. Yeah, we can find that we can replace the silicon by other oxide, but the performance is not so good. Copper silicon is one of the best catalysts for this reaction. Why? Because in previous work, people will claim that, or maybe silicon will help the copper dispose to the with the nanometer. So it's the nano effect. Because the size of the zero nanoparticle is very important. But as we know, when we reduce the size of the copper, we not only enhance the nano effect, but also we enhance the interface effect. How to decompose the nano effect and interface effect? And here, we can solve in another direction. Here we can synthesize the PD powder with the micro scale. Because it's in UL, it's no nanoparticle. Yeah. In this case, no nano effect. Because it's the micro scale particle. Okay. When we count the copper with the silicon, the copper reactivity is very low. When we count the copper with silicon, the reactivity is increased sharply. So it's interface effect rather than nano effect. Here is model. Why? Because the silicon field can match very well with the copper. The binding energy with estimated binding energy is about minus 0.66 eV per silicon. So it's much stable. And the silicon can stabilize the copper 1 plus. Here's the mechanism. Because we use the silicon with the methyl pole. So for similar reaction, we remove some silicon here. This one is silicon, this one is copper. At first, we investigate the hydrogenation dissociation. On the copper surface, the hydrogenation is can be dissociated in the homolytic way. However, at interface, the hydrogenation can be dissociated in the hydrolytic way. Yeah. From the CO dynamic, you can see that the hydrogenation activation on the hydrolytic on the interface is much stable than this one. Yeah. Here we will investigate the hydrogenation mechanism. For the S group hydrogenation, the first step is hydrogen. It's hydrogen attached to the carboxyl group. Yes, it's the best. The transition state is the negative charge, about 0.5 E. So in this case, the hydrogen here cannot help stabilize the transition state. But in this case, because one hydrogen is in the OH group, this one is the acidity of this OH group is very strong, so it can help stabilize the transition state. So the K value for the interface system is about 0.8 eV, and on the pure COP11 system is 1.2. We have calculated the full hydrogenation process for the one acid group. Yeah, here you can see that the black curve is on the COP11 surface, and the orange one is for the silica COP interface. You can see that from thermodynamic view is nearly the same, but from kinetic view, that the interface system can stabilize the transition state rather than the intermediate. Yeah. We also have KIE value. For the pure copper powder system, the KIE, the KH2 to the KD2 is about 1.5. But on the silica copper system, the KIE value is about 2.8. This is 2-fold length. So KIE means the different KIE means different mechanism. Why in this case we have large KIE? Because in this case, not only one deuterium participates on the transition state. This one also participates in the transition state. So this one involves the large KIE. And also, in this case, when the hydroxy group, we can use the sodium hydroxide to remove the hydroxide here. In this case, the KIE of silica copper system will come back to the copper system. Yeah. When the interface has been blocked, it can come back to the copper system. So it can confirm our mechanism. Here, with this understanding, we can design the new catalyst. Here is the copophilic silicon. In copophilic silicon, we have copper oxygen silicon. It's already in this precursor. So when we use this one as precursor, we can make the copper nanotube with very well the copper dispersion. The QF of this is higher than this one, the transition, the conventional one. Yes. And then moreover, we can count the copper nanoparticle with the silicon. Yeah, count it with silicon when we reduce the active side, but we increase the interface side. In this case, we can increase it again. So the silica copper interface is very important by hydrogenation. Finally, we should introduce our recent work in the atomic dispersed PD catalysis. You can see that atomic dispersed catalysis has been well documented in many papers. From physical chemical book, you can see that when we reduce the size of the particle, we will increase the surface free energy. So single atom would have the highest surface free energy. The high surface energy of single atom will make big change to prepare them with very high loading, because high loading would lead to aggregate on the surface. So here we use the photochemistry route to prepare the platinum-1 titanium catalysis. In this case, we use the chloroplatinum acid add to the titanium B. Upon the UV irradiation, we can make the PD1 titanium oxide, the atomic dispersed catalyst. Why? So it's very simple. It's very simple way. But you can make, here's the HRTM. We can see the dot single atom. Here is the substrate. We have not PT bond. And for single atom catalysis, he show very high hydrogenation rate taken for the CC bond. By means of DFT calculation, we can estimate the surface energy. Because to prepare the titanium B, we use the mercy proposed by the Wang Xun from Tsinghua University. To prepare the titanium ultra-thin nanosheet, we add some ethylene glycol. Yes, ethylene glycol on the surface. In this case, the surface energy we can add 2 layers is the most stable. Yes, accordingly, the experiment you can observe here is 2 atomic thickness. It's 2 layers with very large surface area. Yeah. Upon UV irradiation, the surface, upon UV, the electron and the hole will be separated. The electron will come to the titanium, and the hole will come to the oxygen to make an oxygen radical. Because the oxygen radical is less stable than the carbon radical, so it undergo a hydrogen transfer to make carbon radical. Yes, because UV induces radical formation. Yes, this feature has been confirmed by the EPR. You can say this picture is the ethylene glycolate radical. Yeah, we have confirmed this. Here's the full process. The key is the radical species will help to remove the chlorine bond, plenty of chlorine bond, to make the chlorine oxygen. So in this case, the palladium atom can be trapped on the surface. Yeah, and hydrogenation can get this species. And this species also, the structure also include agreement with sulfurs. Yeah. Here's the hydrogenation mechanism. For the hydrogenation on the single atom catalysis, because as we know, the hydrogen usually is dissociated on the metal-metal bond. It requires at least 2 metals. But in this case, we have a single atom system. So the hydrogen is dissociated on the palladium-oxygen bond. Again, it's hydrolytic hydrogenation. We can generate this one is hydride, this one is proton. Yes, this is the hydrogenation for CC bond. Yeah, we will accept such a species, which maybe is very good for CO bond station. CO bond hydrogenation, yes. We also have the CO bond hydrogenation. It's very good. In the experiment, the CO hydrogenation, the single atom catalysis is so 55 times faster than the PT blank. Now finally, we will show that while the single atom can serve as the active site for CO oxidation at low temperature. Why we ask this question? Because for CO oxidation, we have at least 2 sites. One site for CO absorption, and another site for O2 absorption and activation. But single atom have only noble metal site. So can it absorb the active site? As reference, this is the previous report. Some say, oh, CO, the single atom is very good. Others say, oh, no. Nanoparticle is good for CO oxidation. So in our case, we can create the atomic hydro interface. How to create? We can use a cascade. In previous the example, we can demonstrate the electron will transfer to the titanium. Yes? With the cascade, we can make such interface. Here is the HRTM, because it's a photo, with the photo induced, or the radical would have to make a plenty oxygen bond and the electron transfer to the titanium. So after catalysis, we can make titanium, or titanium 3+ and palladium interface. Here. We have, here's the energy, is the energy loss. Is combined with the TM, HRTM. You can confirm this side is palladium and this side is titanium 3+. So we create some unique atomic hetero interface. Here is the example. This is the we can synthesize the single atom through the photo chemistry, photochemical route. This one, and then we can hit in the nitrogen. In this one, our calculation also confirm the spin indicator, which one has been reduced. In this case, it's the titanium. In this case, it's titanium. And in this case, the oxygen, the electron will transfer to the oxygen to make the silk oxide species. And silk oxide species will help to oxidize the CO. Yeah. Here is the mechanism. Here the oxide and CO absorption here, and CO can react with the oxide with all kind of very low barrier, and then CO can react with the oxygen. Here also is very low barrier, and then the final, the CO2 dissociation. Here's the full mechanism. So in this case, it's single atom system with two active sites. One is the palladium, the other one is the titanium 3+. So it's single atom, two active site system. Yeah. Here we like to give a summary. The first one, the surface coordinated chemistry, is very important for understanding the reaction. And the organic ligand modification will be controlled selectivity through the stereotypic way and through the electronic way. And the coordinated chemistry between the metal and spotting will modify the electron state and binding structure of active site, and even to modify the reactive mechanism. And to develop more efficient catalysis with the high stacking and reactivity require better understanding of the organic chemistry. It requires the close cooperation between the theory and the experiment. Finally, we could cite the famous Einstein study. The most incomprehensive thing about the world is that it is comprehensive. We can replace the world by heterogeneous catalysis. We see the heterogeneous catalysis, although it's very complicated, but it can be comprehensive by using the model catalysis and advanced characterization and depth calculations. Here's the acknowledgement. Here's the Professor Nanfeng Zheng is the leader of the experiment. Here the students and me, we discuss every week, so with close cooperation with theory and experiment. Here's a picture of Xiamen University. And Xiamen University is believed to be one of the most beautiful campus in China. So welcome to Xiamen University, and thank you for your nice attention. Thank you.
Thank you very much for this truly outstanding talk. We have time for one or two questions.
Hello, Professor Fu. Chemical group is used to deposit the palladium single atom on the surface of titanium dioxide, right?
Yeah.
And the chemical method used to dope the palladium oxygen in the lattice of titanium dioxide, so as to narrow the band gap of titanium dioxide.
Oh, I'm not sure because it's too difficult. Because in our case, we test different combination. Well, this one is the only fine it works. Yeah. So we don't know why, but this one works. Even we use platinum, it doesn't work.
Yeah, actually we have tried to dope the palladium and particle on surface or some other thing instead of the titanium dioxide. We have not found the red sheet of the band gap, so we think that maybe it cannot dope in the lattice, only on the surface.
Yes.
Hi, thank you. Really nice talk. So at the beginning, when you discussed the ligands binding on the surface, that you mentioned that they make a mesh on the surface. So I guess I just wondering, I suppose they have to leave some part of the metal exposed. So do you have any sense of what is the size or the diameter of the openings that are left for catalysis?
Yes, because it depends on the coverage of the ligand. Yes, it depends on the coverage of the ligand. So because here we can use the bucket with the bucket type, we can leave some room for the reaction.
Yeah, do you have a sense of how big it is?
Yes. We have some channel. Yes. Yes, the coverage is consistent with the experiment determined. Yes.
I would suggest that
Okay.
later. Let's thank all the speakers of this morning session.